My guest today is Professor Emil Martinec, who's Professor of Physics at the Enrico Fermi Institute and the College of the University of Chicago. His research focuses on string theory and particle physics. Welcome, Emil.
Hi.
Yeah, so this is, I've never done this before, Emil. So this is our fourth conversation in a sequence.
Indeed.
And it has been extremely useful for me, and I hope some of our audience. So we started off talking about the four fundamental forces, gravity, electromagnetism, and the strong and weak forces inside an atom. And so there has always been sort of this desire in physics, in cosmology and astrophysics, to unite them together into a singular framework. But we have never been able to do that. In the second session, we talked about Einstein's theory of gravity and quantum mechanics. And these are two theories who are exceptionally successful at the scales that they really focus on. But we haven't been able to bring them together for a long time. And so in the third session, we talked about sort of the objectives of what you're famous for, what you have done most of your career, and that is string theory. And we talked a bit about sort of the history of string theory. So we talked about sort of Einstein's theory and electromagnetism and quantum mechanics, and how the concepts there sort of give some indications that something was missing. Perhaps we can extend it, we can extrapolate, we can go in a different direction. And we talked about sort of the history of string theory, S-matrix theory, 1943, Regge theory and bootstrap models, 1959, 1960s, the dual resonance model, 68, 74, the bosonic string theory and superstring theory, 74, 84. So these are different versions of string theory. But by the time you got to Princeton as a young, charming, I would imagine,
freshly minted PhD, yes.
Kid, let me call you. At Princeton, things were sort of perking back up again in string theory, right? So it's sort of the superstring revolution. So we want to start there, and if you want to sort of connect that to history a little bit, and then talk about what was happening at Princeton between 84 and 94, that's where we will start today's conversation.
Okay, that sounds good. So so what had happened in the period from 74 to 84 was that people were the people who were still working on string theory, as I said, a lot of people, once they realized that quantum chromodynamics was the right theory of the strong interactions, they went in that direction and left string theory behind. And there was just a small cadre of people who continued to pursue string theory and try to understand it better. And as I said last time, Shirk, Schwartz, and Yonea, I think, made one of the fundamental observations that string theory really wants to be a theory of gravity rather than a theory just of the strong interactions. And so one of the things that then became an issue was, okay, if string theory is fundamentally a theory of gravity, how does the standard model fit into it? And of the string theories that were known at that time, two of them, so-called type 2A and type 2B, the terminology is terrible, but anyway, there were...
Yeah, I have to say you guys are really good at naming things.
Sometimes good and sometimes terrible. So this is so one of them were entirely uninspiring names of type 2A, type 2B, type 1. Okay, so the type 2 string theories had gravity, but nothing that looked like the standard model. Type 1 theory had gravity plus gauge theories of the sort that you find in the standard model, but we're missing chirality, what's called chirality of matter. So if you look at, say, the electron or all the particles in the standard model, they have two. If I look at a given particle like the electron, then if it's moving in some direction, it has some momentum. Let my thumb point in the direction of the momentum. Okay, the electron also has spin. And so it can be either spinning left-handed, so if my fingers point in the direction that the particle is spinning, and my thumb points in the direction of the momentum, then what I'm describing right now is a left-handed spin. Well, depending on how your cameras are, if your cameras are reflecting things or not. Anyways, then there's the other orientation where, which according to the way I am in my room right now, is my right hand with the thumb pointing in the direction of the momentum. The direction of the spin is in the opposite direction. So there are two kinds of particles, left-handed and right-handed.
It's the same thing we have in chemistry, right? I mean, we have chirality in chemistry.
Yes, it's in the sense that it's that yes, there can be different sort of configurations of the degrees of freedom, and so there are what are called stereoisomers in chemistry, where there's sort of a chemical molecule, but then it also has a mirror image, which is the same arrangement of atoms, but as if you built them using a mirror. And so it's a similar idea that nature selects doesn't appear in a reflection symmetric way. So for instance, in chemistry, the molecules that are used as the building blocks of life have a particular handedness, and the other handedness doesn't appear in nature, or at least in the cells that make up our bodies. So a similar sort of thing here, except that both chiralities appear, both handednesses of electrons appear. What's different is that the weak interactions that we talked about in previous sessions only couples to the left-handed electron and not the right-handed electron. So just a fact of nature. And so the weak interactions strongly break reflection symmetry in space. And the problem was that this type 1 string theory had didn't have a room for a weak interaction that only coupled to left-handed electrons. And so this was a problem. What was observed in 1984 by Green and Schwartz was that there's a sensitive issue when you have this kind of handedness of interactions, that the theory can be inconsistent quantum mechanically. And so a question immediately arose: if the various string theories are not reflection symmetric, do they have an inconsistency? And what Green and Schwartz showed was that actually the consistency requirements were satisfied by all the known string theories. But that in addition to the known string theories, there was yet another solution of their consistency conditions, what were called at that time the Green-Schwartz anomaly cancellation conditions. Anomaly is this potential inconsistency, and so canceling the anomaly means satisfying the conditions that there is no inconsistency. And so it was seen that there was yet one more potential solution, which in addition had the feature that it would have matter which had chiral interactions with the gauge fields, the carriers of the forces. And so, okay, this is indicated that the fact that there was another solution indicated there might be another kind of string theory that wasn't yet known.
So at that point, sorry, so at that point you have only three: 1, 2A, and 2B. Yeah. Okay. And there was the bosonic string, but the bosonic string had its own inconsistency. It was unstable. It's just not a viable theory. But so of the ones that could potentially be consistent and stable and describe the real world, there were this type 2, type 1, and this potentially new theory that wasn't yet described. And so people in Princeton got very excited. And I had I did my PhD work in part on string theory. So that was at Chicago?
This was at, so my PhD is from Cornell, but my thesis advisor moved from Cornell to Stanford. So I sort of spent half my graduate work at Cornell and half at Stanford. But Stanford was where I met Lenny Susskind, who was one of these progenitors of string theory that we talked about last time. And so I sort of came to Cornell, to Princeton, excuse me, knowing a little bit about string theory, where I also encountered David Gross, who's the Nobel laureate in physics for his foundational work on the strong interactions. But before he sort of built the theory of the helped build the theory of the strong interactions, he was also early in his career a proponent of string theory. So when Green and Schwartz came out with his result, David Gross got interested, Edward Witten got interested. Basically, everybody among the senior faculty in Princeton became quite excited, and the hunt was on for this new string theory that could potentially contain the standard model.
Ed Witten, you said? Yes. So we will come back to him
We'll come back to him. He's a foundational figure in running through all of this, but he became very excited, and so I initially started working with one of the junior faculty at Princeton, a fellow by the name of Jeff Harvey, who's now my colleague at Chicago. And so we started. So what was new about this unknown string theory? It was that the symmetry underlying the gauge interactions, the standard model-like forces, was a symmetry called E8. And there were of the known ways of constructing string theories, there was sort of a no-go theorem that had been shown that groups like E8 were not compatible with symmetry groups like E8 were not compatible with string theory. So so how could this be? There's this obvious thing waiting to be found, some string theory that had E8 as a symmetry, but the known ways of constructing string theories didn't have E8 symmetry. And so, well, we worked on it for a couple of months. I had, because I had been interested in string theory as a graduate student, had been attending various conferences and things related to string theory, and sort of just accumulating, a bag of tricks, if you like. And one of the things in my bag of tricks was that there was a way of using string theory techniques of describing the group E8, the symmetry E8. And so, so when I realized that something I had learned in graduate school was relevant for what we were trying to do in Princeton, we started sort of refining the idea. And eventually the collaboration was my colleague, Jeff Harvey, a person, Ryan Rome, who was a graduate student of Witten's at the time, and David Gross. And together, the four of us hammered out a new kind of string theory called the heterotic string.
So this is the quad. This is a famous quad.
This is the Princeton String Quartet, we were called.
Yes.
And so we came up with this new kind of string theory, which combines elements of the bosonic string, which is unstable, with the superstring. And so it sort of runs the risk of being inconsistent for reasons of instability, but sort of the combination of the fact that it has the superstring, which is stable, and the bosonic string, which is not stable, when you sort of combine the two, the superstring wins and it remains stable, but the sort of bosonic string part of it is capable of describing the symmetry E8. And so by sort of gluing the two together in a particular way, we were able to find something that had all of the right properties to describe the standard model.
So what do you call that?
Called the heterotic string.
Heterotic string.
You say, okay, once again, string theorists with their terminology. So heterotic, this is something that Jeff Harvey came up with. So heterosis is the idea in plant biology that you can take two different species of plant and you can graft one onto the other and get a new species which has better properties than either one that you started with. And so this seemed like a perfect analogy to what we were doing. We were taking two different kinds of string theory, each of which had didn't have the right properties to describe nature. And we sort of married them together, grafted one onto the other to find a new, more vigorous kind of string theory, which had all the right properties to describe the
in some sense, you're also combining, it sounds to me, Emil, it's always dangerous to talk about things you don't particularly know about. But it seems to me that you're sort of combining practice with theory too, in some sense, right?
Well, this is all in a very rarefied theoretical realm. So we're just sort of like playing games, playing mathematical games, piecing together things that we already know how to build as theoretical models, and finding a new theoretical model that was based on two already known theoretical models.
Yeah.
So it's in that spirit.
So this is sort of the fourth string theory now.
Yeah. It had sort of two variants, which it turns out there are various other additional symmetries that string theory has called duality symmetries. And so we initially sort of said, well, there are two different of these heterotic strings, one of which was similar to the type 1, had the same symmetry group as the type 1 theory. And the new one had the E8 symmetry. So people immediately more latched onto the E8 theory because it seemed like initially that was more directly related to incorporating the standard model into string theory. But as we'll discuss later, the duality symmetries that were eventually a feature of string theory turn out to relate all the different string theories in very intricate ways. So that in fact there aren't sort of 4 or 5 different kinds of string theory. There's one kind of string theory that just has different regimes or phases. We were talking about the standard model having 3 different forces that turn out to be in 3 different phases of gauge theory, namely the Coulomb phase, the confining phase, and the Higgs phase. Well, it's a little bit like that. There's sort of different phases of string theory or regimes of behavior, and all the different known string theories seem to fit into this one underlying structure and having different sort of avatars or different phases, which the known string theories are examples of.
So is this, I can quite remember, I know there was a conference at USC. This is where Ed Witten came up with.
Yeah. So that's sort of jumping ahead about 10 years to 1995. So we should probably stick to what's happening in 1984 and sort of work our way up to that.
Okay.
I just want to sort of give you a little sort of whet your appetite for what comes later. Okay. So the heterotic string was discovered. It immediately set off an explosion of interest. So we have to come back to one of the additional features of string theory, which is extra dimensions. So we talked a little bit in previous session about Kaluza-Klein theory and the idea that extra dimensions could be a feature of gravity. So we also talked last time about the consistency conditions of a string propagating throughout a curved space being Einstein's equations. Well, let me actually revise that that discussion a little bit. So a standard method of analysis in physics and in many disciplines is to, if you have something you want to calculate, and it depends on some parameter, some number, okay, like the strength of electromagnetic interactions, say. So the strength of the proper notion of the strength of electromagnetic interactions is something called, well, I don't care what it's called. It's some number. It's 1/137 in nature. Okay, so that's a small number. And so, of course, everything in electromagnetism depends on the strength of electromagnetic interactions. So since it's a small number, you might say, well, let me construct a series of successive approximations to some process that occurs in nature, where the first approximation is the leading order in the strength of electromagnetic interactions. And then I construct a sequence of successive refinements of that first approximation in powers of this small number. So let's suppose I have something in string theory I want to calculate, and my small dimensionless number is 1/10. Okay, so then my leading approximation will be 10% accurate to within 10%. Okay, and so then if I calculate the next order of approximation, it will be accurate to within 1%. And then if I calculate the next order and add that in, I'll get a refinement which is accurate to within 0.1% and 0.01%. So it's like, keep going like that. Okay. So it turns out that this set of consistency conditions I described for a string propagating in a curved space, the Einstein equations aren't the first term in that successive approximation. It's actually the second term. The leading term is the condition that the dimension of space-time is 10.
Is what? Sorry?
10. 9 dimensions of space and 1 dimension of time. So instead of space-time being 3 plus 1 dimensions, space-time in string theory has to be 9 plus 1 dimensions. And if you make that assumption, then the next order in the approximation of string dynamics in curved space are the Einstein equations. And then there are higher terms than that. And the small dimensionless number that you're expanding in is the curvature scale, the scale at which the geometry is curved relative to the string scale. Okay, so if we think of the surface of the Earth, that the surface of the Earth is a sphere, the Earth has a radius which is several thousand kilometers, several thousand miles. So that's the sort of scale of the curvature of the Earth, is the radius of the Earth. Okay, several thousand miles. Okay, the string length is extremely microscopic. Okay, and so the string length divided by the radius of curvature is a tiny, tiny number. And so in nature, this is a really good approximation under most circumstances. And so the first condition is a condition that doesn't involve curvature, it just involves the dimension of space. And says dimension of space has 9 spatial dimensions plus time. And then the next series term in the approximation is, as I was saying, the Einstein equation. So it looks really nice. You get Einstein's equations out of thinking about strings as some fundamental object. But you have to swallow something that looks ridiculous, namely that there are 9 spatial dimensions and not the 3 that we observe. And so this led to a revival of the Kaluza-Klein idea that we talked about before, that you can have extra dimensions of space as long as they're sufficiently microscopic and curled up that we haven't seen them yet with our most powerful microscopes. And so people already knew in the 1970s that string theory had this requirement of wanting to be in 10 dimensions. So already when Shirk and Schwartz and Unea were recasting string theory as a theory of gravity, it was gravity in 9 spatial dimensions. And so they realized, well, nature isn't, but we don't see 9 big, macroscopic dimensions in nature. So we have to revive this Kaluza-Klein idea in order to accommodate what string theory wants space-time to be. And so once you do accept that, then out comes Einstein equations and more. So one of the things that you get is that, okay, Einstein's equations are the first correction to these consistency conditions for strings propagating in space-time. There are subsequent levels of approximation that are additional terms, which are tiny, tiny, tiny corrections, as long as the curvature of space-time is small relative to the string scale.
So let me see if I understand this, Emil. So mathematically, you need to have 9 spatial dimensions and 1 time dimension for string theory to work.
Yes.
And if you accept that, then what we know in sort of the physical, classical way, things seem to emerge from that.
Yes.
As long as you are willing to let go, that you will never be able to see
it's unlikely, yes, that you'll be able to see
the spatial dimensions, right? So, so it's sort of so it's a very elegant way to look at a problem we haven't been able to solve yet mathematically. But then the question remains, if this is only alternative? I mean, are there other ways we can think about this?
Yeah, well, so people since Einstein and quantum mechanics have been trying to marry Einstein's theory with quantum mechanics. And it runs into a number of problems. One I was describing, I think last time, this idea that in gravity, the strength of the interaction is the energy. If you want a dimensionless number, it's the energy relative to the Planck energy. And so as long as you're talking about energies that are less than Planck scale, then the gravitational interactions are relatively weak, and you can calculate. The problem is that when you start doing these subsequent corrections, then you have processes that involve virtual particles whose energies can be arbitrarily large. And quantum mechanics tells you have to include the contributions of those virtual interactions to whatever process you're calculating. And so the problem is that at every step of the approximation, the answers are infinity in gravity, or at least they're of order one. Energies going up to the Planck scale make of order one corrections to whatever you're calculating. And so your approximation scheme starts breaking down because your second correction becomes as big as the previous correction. And so you're adding up a whole bunch of numbers which are all the same order and trying to make sense of it. And so it's like you liked the answer you got in the first approximation, but then you don't like the fact that the next approximation makes a correction which is almost as big as the thing you started with. And so it doesn't lead you to something that converges to a nice answer.
So are we using the extra dimensions as a way to get mathematics to work? That is convergence, avoiding infinities and so on.
So the extra dimensions, the role of the extra dimensions isn't necessarily isn't initially about that. So there are very different kinds of divergences that appear in Einstein's gravity, and the extra dimensions aren't necessarily useful for solving all of them. But the idea that what's more useful for solving the problems of the divergences of ordinary quantum, the sort of naive attempts to quantize gravity run into this problem. So you say, okay, what in string theory fixes this problem? So there's several sort of candidates for things in string theory that solve this problem. The initial one is the idea that if the string length, there's an intrinsic length scale associated with strings, which is the scale set by their tension. We talked about this last time. The energy it costs to stretch a string a certain distance. Okay, so that's one length scale. It's sort of intrinsic to the dynamics of the string. Then there's another intrinsic length scale, which is the one that Planck taught us about, the Planck scale, which has to do with the strength of gravity. And the dimensionless ratio in string theory that you use for an approximation scheme is the ratio of the string length, is the ratio of the Planck length divided by the string length. So the string length is the string length can be much bigger than the Planck length. And so say if it's 10 or 100 times bigger than the Planck length, then you have a small dimensionless number. The ratio of those two scales is 1/10 or 1/100th, and you have a scheme for approximating things. So you could say, okay, how does string theory solve the problem? Well, because once you start reaching energies which are the string scale, which is below, so the interactions would become strong if they looked like gravity all the way up to the Planck scale. Okay. But the problem is that as soon as the energy gets up to the string scale, you start exciting the vibrations of the string. And so the nature of the interactions changes from that of particle physics because you have this extended object. And the extended object ameliorates the divergences. It sort of takes over the dynamics and says that gravity is just one of many kinds of different vibrations of the string. And because there's sort of this democracy of all different vibrations of the string, of which gravity is just one, gravity gets overwhelmed by everything else, and the divergences are less severe. And so that's the way we understand, at least within the context of these successive approximation schemes, that string theory is a finite theory of gravity. That is, it doesn't have these wild, uncontrollable corrections to dynamical processes.
So, as you say, the democratization of strings vibrations that produces gravitons and other things sort of puts things in the context or put gravity in its place, so to speak. Yeah. Is that the way to think about it?
Yeah, so exactly. So for instance, there are certain kinds of singularities in the geometry, what are called curvature singularities. So I said if the curvature is weak, everything is nice and well controlled. But one of the features of Einstein's theory is that the dynamics of the theory can create, as time develops, can develop regions of high curvature. Just as things run around and interact with each other, you can generate singularities in the structure, in the curvature of space and time. So the singularity at the core of a black hole is such a curvature singularity, where Einstein's theory breaks down. And there are various other kinds of curvature singularities that can also occur. And some of the singularities are resolved just by accessing this large space of string vibrations. Other singularities, such as the black hole singularity, require more what are called non-perturbative effects that go beyond the successive approximation scheme and treat the dynamics more exactly. And we'll get to that in a little bit. Yeah. But there were at least, already in the late 1980s, it was understood that string theory was good for fixing up the shortcomings of Einstein's theory. Remember, I said there were these successive terms in approximation, which are related to what is the ratio between the length of strings and the radius of curvature of the geometry. So when the radius of curvature becomes of order the string length, then this sequence of approximations starts not working so well. But there are various techniques for dealing with the dynamics going beyond the approximation scheme and solving the dynamics more exactly. And it was seen that in those exact treatments, the sort of extra structure of string theory fixed the problem of Einstein's. By going beyond Einstein's theory, you fixed some of the singularity problems of Einstein's theory.
It's really fascinating, Emil. So would you say the beauty of string theory is that it is sort of a modified theory of gravity, and then standard model comes for the ride?
Yeah, so we haven't talked about how the standard model comes out, and it comes from this Kaluza-Klein idea.
Yeah.
So, there are 6 more dimensions of space beyond the ones that we observe in the world, and so they have to be tiny. So the question becomes, okay, so you more than just saying, okay, they're tiny, so for all practical purposes, I won't have to think about them. Well, the way they enter particle physics is that in the string idea, every particle is a particular kind of state of strings. Underlying it, the particles are actually strings at some microscopic scale. And so when you say, okay, what's the mass of a particular particle? The mass of a particle gets a contribution from what the string is doing in the extra dimensions. And so to figure out what the spectrum of particles is in the standard model, you have to solve for the dynamics of strings in this tiny compact space. And the ones that are light are the ones where effectively the dynamics of the strings in this tiny compact space gives you almost zero contribution, or essentially zero contribution to the mass. And so
like neutrino, for example?
So for instance, the neutrino, but actually all the quarks and electron and everything, okay? So the gauge bosons are protected from getting a mass because of symmetry reasons. But the particles of the standard model don't have any obvious way of keeping their masses light. So if you're saying, okay, the dynamics of strings, affects everything, then you would say, okay, well, what's the natural scale for masses of particles? Well, it's the string scale. So obviously, and the string scale is like the compactification. These are all very microscopic scales. So we have to do something. We have to engineer something in the theory that keeps all the particles of the standard model much, much lighter than the scale of the compactification. And so there are various mathematical effects, things called topology, topology theory, and properties of geometry, let's just call them, which guarantee you a certain spectrum of massless or light particles. And so what string theory does is it converts a problem that you had before, which is what is the standard model? What are the interactions of the standard model? What are the particles? What are the masses of the particles and their spins and so on? The data which in the standard model of the 1970s is sort of input. You have to say, that's just the way the world is, and I'm not allowed to ask the question, why is that? Okay. In string theory, that's output. Namely, that you have to choose, you have to figure out what the structure of this compactification, this tiny compact manifold is. And the geometry of that tiny compact manifold tells you what the masses and structure of the particles of the standard model are. So a question you weren't even allowed to ask in the standard model gets turned on its head and turned into a question about geometry. And the question now becomes, why is the geometry of the extra dimensions in string theory precisely the thing that has the spectrum of particles that we see? And so it's sort of both a problem and an opportunity. It's an opportunity to explain why, but it's a problem because you have to solve Einstein's equation on this 6-dimensional space. And there are many, many such solutions of Einstein's equations. So the question now becomes, why are we living in the particular one that has the particular spectrum of light particles that we see in the world around us? And that's a problem which has been sitting with us since the mid-1980s, for which we still don't have a good answer.
So in some sense, it's a visualization problem. So early last century, Einstein imagined things, and it was imaginable because we have a Homo sapien brain that lived in 3 dimensions forever. But now it is still an imagination problem, but we don't really have the intuition for that imagination. Is that fair?
Well, to some extent, yeah. It's hard to visualize 6-dimensional spaces. I mean, you can't draw them.
I do that for breakfast every day.
The paper you would try to draw them on is only 2-dimensional. So we have enough time, making architectural drawings of 3-dimensional things using 2-dimensional blueprints. So imagine trying to construct the engineering blueprints for a 6-dimensional space needed to describe string theory. It's just, I mean, we're a little bit at a loss. And so what people end up trying to do is to say, well, let me describe the 6-dimensional space, making 2-dimensional slices of it, and those we can draw. And so people tend to do that sort of thing.
But that's not satisfactory from sort of holistic understanding of the thing, right? So I want to go forward in time. So we have, as you mentioned, 1, 2a, 2b, and a couple of other types of string theories that you mentioned. Mm-hmm. So we have sort of 5 different string theories going on.
Right.
It was getting a little bit confusing, right? By mid-90s, things were.
That's right. That's right. So what had happened in the interim was, so we were all very happy and patting ourselves on the back that we'd found a home for the standard model within gravity at the expense of this extra dimensional theory, but with the benefit that it seemed to solve some of the problems of Einstein's theory when it came to gravitational singularities. But no explanation, for why exactly this particular tiny manifold, and which remains a problem to this day. But the idea now, has become that in some sense everything is made of strings. The particles of the standard model are particular vibrational states of the string. The three forces, strong, electromagnetic, and weak, are different manifestations of the string, and gravity is another manifestation. So it's like, it is a unifying idea that everything is somehow made of this one object. But certain things still didn't click. And one of the things that we still didn't understand was there are certain kinds of singularities, in particular the singularities in the middle of black holes, that didn't seem to be resolvable using this idea of strings, a bigger space of excitations coming out of the strings themselves. And there was another sort of hint that was lying around, but a lot of people weren't paying enough attention to, which was that there were, in the type 2 theories, there were additional Coulomb-like gauge bosons, additional Maxwell-like gauge theories, which had a funny property. They weren't Maxwell's theory because it didn't seem like there were any objects which were charged under those forces. So it was like you had a photon, but you had no electron. And so, but it's like, what is this doing in the theory? Because remember when we were talking about the way the forces work, was that you had charged objects like the electron, and when you shake that charged object, you disturb the electromagnetic field around it, and the electromagnetic field sends off a stream of photons. And so, what is the use of having a photon with no charged particles to make it? And so, so people weren't thinking about that because the type 2 theory didn't seem to have any room for the standard model, as I was saying earlier. And so people sort of said, it's just some string theory that doesn't have the standard model, and why should I care that it doesn't have charged particles? But one person was paying attention, and that person was Joe Polchinski, who was, I guess, initially at University of Texas and then University of California, Santa Barbara. And so he realized that that there actually were objects that were charged, and they were a completely new thing that people hadn't realized were in string theory, called D-branes. And they're even weirder than string. String you think of as like one little vibrating loop of energy. The D-branes come in all kinds of different shapes and sizes. So there are D particles, there are D strings, there are D membranes, there are every dimension of object you can imagine, all the way up to filling the entire 9 dimensions of space. And it turned out that the type 1 theory was actually just a theory in which there was a D-brane around which filled all the 9 dimensions of space. And so that got people very excited because, okay, you have new toys to play with. What can you do with them? And one of the things that people realized was that you can ask this question of if strings, the strings as we were sort of visualizing them up until Polchinski's observation, we were always doing calculations where we, again, expand in a small number. So the small number was the ratio of the Planck scale to the string scale. But you could ask the question, what happens if we're just playing mathematical games. What happens if we take the ratio of those 2 energy scales and we make them, equal to one another? Then there's no small parameter to expand in. And strings are strongly interactive. It looks like you get back the problem with quantizing Einstein's theory. Namely, what fixed the problem of Einstein's theory? It was all these stringy vibrations which started entering the dynamics before you got to the Planck energy. But if you now make the string energy scale and the Planck energy scale the same, then don't you get back into the same problem? And the thing that fixes that are Polchinski's D-branes. That if you crank the string energy up to the Planck energy and actually try to even make it even bigger than the Planck energy, so there are no stringy vibrations below the Planck scale, then what you find is that one of the D-branes that you thought was a heavy excitation, as you're doing this dialing of the interaction strength to be, big, the D branes get lighter and lighter. And so what happens is what you thought were the string excitations and what you thought were the D brane excitations change places. And so there's never a regime in string theory where the coupling is the interaction strength is large. It can at most be order 1. And when you sort of dial around in the strengths of interactions, different objects become light. Okay. And so it was not long after Polchinski discovered the D branes that sort of Witten and 2 other physicists, Hull and Townsend, observed that there was kind of a unity of string theories, that in fact these different string theories that were thought to be different, just different. You had to make some choices at the beginning to say which string theory was relevant and then go with that one. Instead, no, they're different regimes of behavior or different phases of one bigger theory. And the one bigger theory has both strings and D branes and actually other kinds of branes. But they were cataloged, the different kinds of branes and strings that can appear. And so there's sort of like this one object whose mathematics we still don't completely have under control. We still call it string theory. We sometimes also call it M theory, because one of the corners you can push the theory into the thing that there's nothing that becomes light and takes the place of the string. It's just the interactions remain at the Planck scale, and the sort of extended objects in the theory are 2-dimensional and 5-dimensional. And so it's sometimes called M theory because M is for membrane. And so the simplest extended object is not a 1-dimensional string, but a 2-dimensional membrane. That's what's called M theory.
So it's not a 1-dimensional string, but a 2-dimensional membrane. So, I'm going back to sort of the quarks. The particles are sort of coming out because of the vibrations of the strings. Now we have a 2-dimensional object.
Right.
How does that fit with, so how do we explain, I mean, at least without knowing anything about it, it sounded like it's feasible to have some sort of microscopic thing, sort of vibrating to create particles.
Yeah.
Now we have a 2-dimensional thing. How does it fit?
So, so there are various ways of getting this. So once there was realized that D branes were important to the underlying structure, and these other branes of M theory and so on. So then the question becomes, okay, yeah, let's go back to this question of how the standard model of particle physics arises from string theory, and one of the things that came actually the way that Polchinski actually got at these idea of D branes was by thinking about the dynamics that D branes support. How do strings interact with D branes? And so by thinking about how strings interact with D branes, there's sort of there's a way that a graviton, for instance, can come in and latch onto a D brane and sort of split apart. And the ends, so what was a little closed loop of string becomes a string which has 2 endpoints. And it turns out that living on the D brane, some of these what are called open strings, or little segments, which have ends, the ends are trapped on the D brane. And so there's sort of a dynamics that's intrinsic to the branes themselves. And you say, okay, what is that dynamics? It turns out to be yet another Maxwell type theory, or strong interaction type theory. In other words, a gauge theory with some underlying symmetry and some underlying matter degrees of freedom. And so another home for the standard model to come out of string theory is the dynamics of the branes themselves, in addition to the dynamics of the geometry of the extra 6 dimensions. You could have branes that are, say, filling our 4 dimensions of space and doing something in the extra dimensions. And the dynamics on the branes will fill the 4-dimensional space with, the particles that live on the branes. But since the branes are filling four-dimensional space, you'll have particles that can be anywhere in space because they live on the D brane.
So more simplistically, Emil, can I think about the D branes as sort of a stage on which the strings play?
Yeah, the D branes can live on the strings can live on the D branes. That's a description of the brain dynamics. Again, when the coupling, when this small parameter is small enough. But intrinsically, one should think of it as that there are many places where the standard model can have a home. It can be in the geometry of the extra dimensions. It can be in the intrinsic dynamics of the brains that live in space-time. So it's sort of like enlarged our toolkit for building the standard model as an ingredient of string theory.
Yeah, it's beyond me, but I can get some sense of it.
Yeah. And well, so I think the way you should think about it is that string theory has a sort of what I would call a protean character, not protein in the sense of amino acids, but a protean in the sense of the Greek god Proteus, who was one of the sea gods. And his superpower was being able to change his shape at will. And so string theory is like that. There are all these different branes and strings and other exotic objects. But as you go from one regime of behavior into another, the branes become strings and the strings become branes and particles become other things. And so, it's hard to say what the fundamental degrees of freedom are of the theory, because which are sort of the lightest excitations and what are they made of changes as you go around to the different regimes of the theory.
It's also clouded by our ability to observe things. So yes. We observe some things and we attribute some information to it.
Right.
But beyond that, there is so much going on that information may not be sufficient. Yeah.
So we're going to have to develop new intuitions, and in part because what this protean substructure is doing is it's changing our notions of what space and time are on the most fundamental length scales. And the way, for instance, that can happen is that there's, as I was saying before, there are these sort of immutable properties of geometries called topology. And so the topological properties were thought to be things that you can't change by deforming the shape of the manifold however you like. And what string theory shows is that you can actually smoothly deform one topology of manifold into another by making the geometry singular. What happens when you reach a singularity is these other extra objects, the strings, the branes, etc., some of them become light. And when they become light, they can condense. It's a little bit like we were talking before about phases of matter like steam and water. Well, how do you get water out of steam? You condense the water molecules out of the air and you make this different phase called water. So it's a little bit like that when you twist up the shape of the extra dimensions and you make them singular, then different kinds of strings and branes that are wrapping the topology can become light and in fact massless, and then it costs you no energy to make lots of them. And what you find is that when you make lots of them and you make a big condensed soup of this new light stuff, what you've actually done is to change these topological characteristics, which were thought to be immutable. So when I said before that in the heterotic string, getting the standard model out was choosing the topology of the compactification, the tiny 6 extra dimensions. You might ask, well, don't I have to make that choice at the beginning? Am I back to the problem of the standard model of why the forces are the way they are? And the answer is no. It's a dynamical question. I can start with one compactification that has one spectrum of light particles, and I can smoothly deform it into the one that's the standard model one by a process of making certain strings and branes and extra things light, condensing them, and turning them into the standard model.
So is it really dynamic? So this goes back to a couple of things we want to talk about. One is the Big Bang. So is it really dynamic over time that things can change completely?
Well, it's probably not dynamic anymore. It might have been dynamic at the Big Bang when you had a big hot soup of all of these things. But eventually you sort of settle out into something. In the same way that, if in the Schrodinger's cat experiment, where you create an electron that's simultaneously spinning this way and this way, and then you measure it and you decide what to do with your cat based on whether the spin came up or down. When you started off with the electron, it was in both. It was in a superposition. It was in a state which was neither up nor down, but some mixture of the two. Okay. By the time you do the measurement and decide what to do with your cat, then those two outcomes of whether the spin was up or down, those sort of bifurcate into two different branches of the quantum mechanical wave function that subsequently never talk to each other. And so while the universe might have early on been a mixture of many of these different compactifications and topologies and whatnot, eventually it settles down. And we presumably, so there may be other branches of the wave function that are off doing different things and having different versions of the standard model. But we'll never talk to those regions of space because the experiment has already been done. And we settled into one branch of the wave function in which our standard model lives. And the rest of them, for all practical purposes, are the purview of metaphysics.
So this is so disappointing, Emil. Are you telling me that there is a version where Donald Trump was not the president?
It could well be, and would that we lived in that version. But it's not to be.
Right.
But at least again, it becomes a question of all these things which you thought were things that you have to decide a priori in order to set up the initial conditions of physics, all of a sudden become dynamical questions in string theory. And we have to be smart enough to understand that dynamics well enough to understand cosmology and other phenomena like black holes.
So yeah, so I want to finish up with black holes. So the only sort of experimental laboratory that you have for string theory, maybe not the only one, but a good one, is a black hole.
Mm-hmm.
And if you were to prove something there somehow, then things get interesting. I read something, Emil, that so the background microwave radiation, perhaps we can find some signs of strings. Is that possible? Just before the inflation, you get some small.
Yeah, well, so it's one of these things that you want to explore just in case. It turns out there are vestiges of string theory living in the pattern in the microwave background, but don't bet the house on it because the likelihood of that not having happened is equally larger. So it's always good to look around and see, is there some faint residue of the early universe that in the microwave background that would teach us something about string theory? And the answer is maybe. So let's go look for it. But I would not be surprised if the answer to that question was no, there isn't anything that we can reliably detect in the microwave background. The one place where we're really forced to confront the shortcomings of general relativity is in black hole physics, because that's a place where Einstein's theory is just guaranteed to break down. It's the formation of black hole is sort of an instability that when stars are first born and are shining brightly, they shine brightly because they're burning thermonuclear fuel. They're fusing hydrogen into helium. and creating energy that way, which makes all the atoms hot. Okay, and hot gases exert pressure, and the pressure is a counterbalance to the force of gravity trying to make everything collapse. And so stars are perfectly happy for billions of years burning their nuclear fuel, but eventually they run out of fuel. And if they're big enough when they run out of nuclear fuel, then nothing can stop them from collapsing. And so a large fraction of the matter in the star goes, rushing in towards, well, everything goes rushing in towards everything else, and nothing can stop it. And gravity gets stronger and stronger. The more compact things are, the closer they are. The Newtonian force is inversely proportional to the distance. So the closer you make things, the stronger the gravitational force is. So everything just runs away. And the compression of things under the force of gravity becomes infinitely strong in a finite amount of time. And so that's a breakdown of Einstein's theory, because nothing is truly, look, either there's just, a failure of physics and nothing fixes it, or there's something that takes over from Einstein's theory and fixes this problem of infinite compression of matter. And so, well, string theorists say, well, we kind of have a neat little toolkit for you to play with. All these extended objects, which already fixed some of the singularity problems in Einstein's theory. There were certain singularities that were already resolved by string dynamics. And so, so the question is, does string theory also have the capacity of fixing this runaway singularity in the core of black holes? And I think, there's lots of evidence now accumulated since this second string revolution in '95, when we understood that there were D-branes and that all the string theories were part of a big, larger construct. One of the things that came at that time were the first calculation by Strominger and Vafa, and a related earlier one by Ashok Sen in India, that showed that you could account for some of the properties of black holes within string theory, certain special black holes, I should say, within string theory. And there was a plausible generalization of that to generic black holes, where the same ingredients would describe what was going on when you formed a black hole.
Yeah, this has been fascinating, Emil. I don't think I understood most of it, but it's still really interesting. So we have this challenging problem in front of us, which is sort of the grand unification idea. There are no alternatives, it appears to me. Correct me if I'm wrong. String theory is the only game in town from a unification perspective, isn't it?
Yeah, well, so some people like to explore other avenues for quantizing gravity. I think most of them are more conservative than string theory in some respect. That they basically are still trying to take Einstein's theory and apply the things that worked well for the other forces in the standard model, and just say, well, maybe we just haven't been clever enough in our approach to using the standard tools to quantize gravity. And one of these approaches is something called loop quantum gravity.
Yeah.
And so loop quantum gravity, one thing it does is sort of, the loops are not strings, the loops are something else. But one of the things it does is it sort of treats space-time as something that's discretized. Yeah. And the problem when you try to discretize space-time is that, remember I said earlier that the electron comes in two types, so it's sort of a left-handed part and a right-handed part, and the weak interactions only talk to the left-handed part. And that's a problem when you try to discretize theories of particle physics. That there's a theorem that says you can't put left-handed interactions in a discrete space-time. And so it may be that there's a way of fixing this problem in the approach that people are pursuing in loop quantum gravity. Any of these approaches are all speculative. They each have problems. The problems that different ones have are different problems. And each one can point fingers at the other and say, your problem can't be solved and my problem can be solved. And so, I'm just pointing out one problem that loop quantum gravity has that string theory doesn't. But, the loop quantum gravity people will point to string theory and they'll say, oh, well, you have this problem of choosing the extra dimensions or figuring out the dynamics. And by the way, none of you have solved the cosmological constant problem. So, there are any number of complaints one can have. We all have our prejudices as to why our theory is the most promising one. And I've described for you why I think string theory is the most promising one.
Yeah, so just to conclude on this, so is my intuition right? There are two opposing theories. My intuition is that take quantum mechanics as a given and find out how gravity fits into it. It's a bit like, if you're flying over Chicago and I look at all the buildings and I see the geometry of Chicago, but I have no clue, concrete, steel. I was a civil engineer, so that's why I'm using the terminology. How do those materials, sort of come together to make this cityscape? I will have no clue. I'll see the geometry, beautiful geometry of the city of Chicago. It seems to me that quantum mechanics is really fundamental. But when we take ourselves away to some distant point, we can see some interesting features of geometry. But that's really fundamental. That's my intuition. What would you say to that?
So it's interesting that you have that intuition because so one thing that came out of this second superstring revolution and understanding some of the microphysics of black holes was precisely resolving this question of how are black holes consistent with quantum mechanics. And so one of the key observations in that was something called the gauge gravity correspondence. And so I don't know if you want to spend time going into that a little bit, or I can sort of cut this out. So the idea is that if black holes are described by particular by these D brains, if some of the important ingredients of black holes are these new objects that were discovered, D brains, and the D brains have their own intrinsic dynamics on them. They have this like standard model gauge theory dynamics on them. And so I can think of a black hole kind of as two different things. I can think of it as a gauge theory living on a D brane, or I can think about it as the geometry that is coming from gravity. And while the usual paradigm of physics is there's matter and matter sources geometry, this gauge gravity correspondence was more of an either or, that in taking a certain limit, you could either describe what's going on as gravity, or you could describe it as the gauge theory on the D branes without gravity.
Yeah.
And so this leads to an idea that, and so as people sort of began to absorb this and play with it more and more, and try to abstract the lessons of that second string superstring revolution, they began to ask the question: okay, if there's an alternate description of the black hole and the things around it that's not based on gravity but just the gauge theory living on D branes, I've sort of replaced gravity with the quantum mechanics on these brains and the quantum mechanical theory that lives on these brains. So it's a description of things that behave like gravity without having gravity in the description. Yes, there's this other description, which is gravity, but there's an alternative which doesn't have gravity in it. And so people have been playing with that idea for now almost 25 years. And it's led in some surprising directions. And one of them is precisely what you're saying. Can we sort of just assemble some quantum mechanical degrees of freedom, lots of them, and have them interact in sufficiently complicated ways that geometry sort of emerges from that soup? It's just some soup where I put in quantum mechanics and some interactions and stir. And in the end of the day, sort of the long distance behavior looks like gravity. So gravity is then in what's called an emergent phenomenon from something more microscopic, which doesn't have gravity as an a priori feature. And it very well could be.
Yeah, ignorance is very dangerous, but I like that a lot, Emil. At least it sounds plausible to me. Excellent. Yeah. So I think we covered so many things that I had no clue about, but then it has been quite interesting.
Yeah, well, I hope if people weren't enlightened, they were at least entertained.
Excellent.
What those crazy guys are thinking about these days in theoretical physics.
Excellent. Thanks so much for spending so much time with me, Emil. This has been great.
My pleasure.
Thank you.
Oops, I can't hear you now. I can't hear you now. Do I need to restart my audio daemon again? Let me do that again.
Can you hear me, Emil?
Yeah, I can hear you now.
Sorry. Yeah, so I published 2 of them. And
yes, I saw your note on the link to the second one.
Okay. So I published this in the next couple of days. I think this has been exceptionally good. I learned a lot. Hopefully somebody else would have.
Yeah, I tried to put at a level where I wasn't using lots of math and jargon and so on. So I hope that came through. That people that don't have the math and physics background will still be able to take something away from it.
Right. Yeah, I mean, one goal is to sort of aspire, get people aspired to physics.
Yeah.
Get people in this field. I mean, there's so much to learn here. So I don't know. I mean, hopefully we'll accomplish something.
Yeah.
But thanks again for all your time.
Yeah, it's been fun. It really has been fun. And thank you for reaching out again and setting this up.
Thank you. Stay safe.
And by the way, if you ever find yourself in Chicago, look me up.
Yeah, we have to get a beer together. Yeah, so I will. So my daughter is going to Case Western for her residency.
Uh-huh.
So I'm going to be traveling to Cleveland more often than the East Coast. So I'm pretty sure I'd come up to Chicago.
Okay. Yeah. Where are you based?
I'm in Connecticut.
Ah.
Yeah.
Okay.
So so I left Chicago a long time ago, and
you're East Coast.
Yeah. So yeah, I would love to. I'll ping you. If I come to Chicago, and we can maybe get a beer together or something. And
that would be great. That would be great.
Excellent. Thank you.
All right. Take care.
Bye.